Well, welcome everybody to the National 303D TMDL Webinar Series for January 11th, entitled Using Climate Change Informed Precipitation Metrics for Water Quality Planning. Our presenter today is Michelle Miro. I'm your moderator, Richard Friesner from NEIWPCC. And NEIWPCC, we're a regional commission that helps the states in the Northeast preserve and advance water quality. With support from EPA, we've been running this webinar series since 2016 as part of our work to develop, coordinate, conduct, and train programs and staff that serve water quality professionals regionally and nationally. As always, the presentations in this series represent the views of the speakers and don't necessarily reflect NEIWPCC or EPA endorsements or positions. So a couple of note here that after the webinar, you'll be prompted to complete a short survey. We do appreciate your feedback, so please provide it to us at that time. Looking forward for that. Sorry, a lot of screens here. I'm doing my best. If you'd like to propose a webinar, we'd love to have you do that. Our priority topics in recent times are climate change, HABs, cross Clean Water Act program collaboration. We do have funding available for eligible applicants, and the application is rolling. You can submit that at NEIWPCC.org/303D-TMDL-webinar or contact me for additional information. We also have a great series of archives, and these archives are available on our YouTube channel, which you can access at the link provided here. This includes all of the National 303D sessions, so this one will also be up when it is prepared and ready, which should just be in a couple days. So without further ado, I'd like to begin our session. And I'll also tell you that we have several opportunities for questions throughout the presentation. And our first one will be here. We'd like to get a little information about the people in the session. So I'm going to launch a poll and give you a little bit of time to respond. This has 2 questions. Just looking to get close to our number here. I'll give you a few more seconds to respond. And while I do that, it would be great if during the presentation, you could ensure that you are muted and that your camera's off except for our presenter. If you do have questions, go ahead and as we go along, put those in the chat and we'll do our best to get to them at the end of the session. Okay, I'm going to end the poll here and I'll share the results so that you can see where we've got people coming from, quite a few state government, federal government, and tribal, which is great, and municipals. And it looks like for number 2, a lot of people from the Northeast, Northwest, Southeast, and Southwest, and then not from the conterminous United States after that. Okay, so let me admit a few more people. Without further ado, I'd like to introduce Michelle Miro. She is the Water Resources Engineer at the RAND Corporation with a broad portfolio of work that supports international, federal, and local emergency infrastructure and resource management agencies with climate adaptation, disaster resilience and recovery, and water resources planning. She's a co-investigator for the National Oceanic and Atmospheric Administration's Mid-Atlantic Region Integrated Science and Assessment Program, where she leads climate adaptation's stormwater management research. She holds a Ph.D. in civil engineering from UCLA. Michelle, take it away.
Thanks, Richard, and good afternoon, good morning for all of y'all. I'm on the West Coast for all of you out here. I'm going to go ahead and share my screen. So just bear with me while I get this up. So today I'm going to talk through really an example of how to think about incorporating climate change into infrastructure design standards. And this is a project that was carried out in partnership with a range of entities, which I will go through in a second, but is intended, like I mentioned, to really be a case study. So I'm going to talk through especially the climate projected data we used, how we pulled that into design standards for stormwater, how we thought and communicated uncertainty in future climate, and how we wrap that together into an interactive tool. So there'll be two parts to my talk today, the kind of meat and potatoes of what we did and the methods, as well as a quick kind of tour through the tool. If you have questions throughout, as Richard mentioned, please just put them in the chat. I actually won't monitor the chat during the talk. I just have a laptop here, but we'll get to them at the end. We should have, plenty of time to address at least some of the questions. I know there are a lot of y'all on the line today. So in terms of the project, I just like everything else, I did not do this alone. So I worked in a team, and I just really want to acknowledge them and our funders before I jump in. So I work at the RAND Corporation. We're a nonprofit research institution, and we run the MIRISA program, as Richard mentioned, which provides applied policy and climate adaptation work to the Mid-Atlantic region. And I serve as a co-investigator on that. My co-lead from RAND, Dr. Krista Romita Grohalski, was also involved. But then we had two really core partners on this work, Dr. Costa Samaras, Dr. Tania Lopez Cantu from Carnegie Mellon, and Marissa Weber, graduate student, and then Dr. Art Digatano from Cornell and his team. So just wanted to acknowledge there that they contributed very much equally to this work, and I am just representing the team today. And then just, to thank our funders. This work was funded by the Chesapeake Bay Trust under the Bay program, and then was also extended to the full state of Virginia, and I'll talk about that throughout, by two additional research centers. Okay, so let me just hide some of this so I can see my full screen. Okay, so this work was really motivated by something y'all are probably seeing in many of the regions you represent around the United States, and that's precipitation is changing. And in particular, in the region of interest for this work, the Chesapeake Bay has seen increases in precipitation over the past decade. And then when we look to climate model data that projects these changes into the future, we see that they're anticipated to grow by the end of the century. And this figure here on the right is an analysis we did as a part of the MIRISA program that just looks at the projected change in average annual number of days with precipitation above 3 inches. Anything that's dark green is essentially a doubling of the number of days with extreme precip for this region. And so these types of changes are problematic because they affect infrastructure design, they affect our ability to manage water quality, they affect a lot of things. And this was one of the driving motivators for the work, is that to design and build infrastructure assets that are supposed to last into the future, manage water quality, manage stormwater in communities, they need to reflect future precipitation projections and not be solely based on what we've seen in the past, particularly given that what we've seen in this region over the past decade is those changes from recent or from historical patterns have been pretty significant. believe many of y'all will be aware of what IDF curves are. So bear with me if you do know. If you don't, just want to give an overview for those of y'all who aren't familiar, because I'll talk about them a lot for the rest of the talk. So one way of designing to precipitation are through IDF curves. IDF curves are the relationship between the intensity of a precipitation event, often the depth, so 2 inches, 3 inches, 4 inches, the duration, so how long it lasts, 15 minutes, 24 hours, and its frequency. So if you've heard of the 100-year storm event. And they're used to, they're used in permits, they're used in design standards, and they're based, that relationship between intensity, duration, and frequency is based on a statistical analysis of historical rainfall. This is just showing an example of that relationship, showing, apologies, it's in millimeters instead of inches, which we probably all use. But just showing what that relationship looks like. So you have duration here on the x-axis, rainfall depth on the y, and then these curves, the IDF curves, show the different frequencies. So the 100 would be the 100-year storm event, and the 1000 would be the 1000-year storm event in this example. Again, just a refresher, so we're all on the same page with IDF curves. The development and use of IDF curves have been standardized across the US, mostly through NOAA's Atlas 14. And Atlas 14 is really the primary source of IDF curves used by departments of transportation, by stormwater agencies, by various entities around the United States. In the region we're looking at, Atlas 14, as I mentioned, most of these methods are based on historical rainfall. In the Chesapeake Bay watershed, Atlas 14's volume 2 is used, and it doesn't incorporate data after 2000 in the generation of those IDF curves, which is problematic, given that we've seen, as I mentioned, recent changes, especially over the last decade, in precipitation in that region. So these IDF curves that are being used for design aren't reflecting even current climate conditions. One of the other challenges with part of the methodology that underlies Atlas 14, or really just the use of historical data within it, is this idea of a stationarity, and it relies on an assumption of stationarity. It's probably a term many of y'all have heard in the past. Many of you probably know its definition, but just for those who don't, stationarity essentially means that an assumption that the variability we've seen in the historical record will continue into the future. And in some cases and in some areas, that assumption can still hold, and there are tests you can do on precipitation time series to understand if stationarity, the assumption of stationarity is still valid, but in much of this region, we've seen that it isn't. So this is also problematic for the region. I'm just going to go to the next slide because I've kind of talked to that point already. Just again, not to kind of harp on this point about Atlas 14, but I really do like this study, and I like to bring it up in talks like this. One of my colleagues at RAND, as a part of the MARISA program, worked with the city of Pittsburgh and looked at, among many things, how Atlas 14 fared in the recent past. So what this figure shows in green are the expected count of 2, 5, 10, 25, et cetera, year precipitation events in this particular sub-watershed within Pittsburgh, and according to Atlas 14. So this would be the, I think, 2-year storm event. It was over a 16-year period, so you'd expect to see it 8 times. So that's how you read that first column. If you look at actual data for this particular watershed, they experienced that 2-year storm 18 times. So again, if you're managing for water quality, for stormwater, this can be problematic. You can see exceedances, you can see inundation because of this. So the motivation is really, how can we make and support the region in making IDF curves reflect future climate and not just based on historical data sets. So what we did is developed future projected IDF curves for the entire Chesapeake Bay watershed and Virginia. The watershed, for those of y'all who aren't familiar with it, covers part of Virginia, but not all of it. And so Virginia asked us to extend the work to the state. So that's why you'll see this kind of appendage of Virginia in a lot of the figures and in the tool that I'll show later. And we put all of those into an interactive web-based tool where people could download these projected IDF curves to be used in design. And again, this is not meant to be a presentation that's kind of prescriptive on how to do this, but instead show options of how you can think about integrating future projected climate information into existing design standards, into existing processes and metrics that you're using. So I'm going to focus on the aspects of the work that could be flexible to other approaches and things beyond IDF curves. Okay, so in developing our tool, we wanted to make sure we were supporting the development of more resilient infrastructure. We wanted the tool to be user-friendly, so people could easily access it, but also understand the changes that they're seeing. So I'll talk through that. And then we wanted to also, we wanted the tool to consider uncertainty. We know that there is no single best estimate of the future. If we're standing today, we can't predict with 100% precision. And so best practices in climate adaptation consider a range of future climate projections. So we wanted to provide that range so users of the tool could understand what their full potential risk could be and what the full range of projected changes to these IDF curve values could be. So I'll talk about that a bit more as well. Okay, so into some of the nitty gritty of what we did. There's a lot of steps here. I'm going to just, as I mentioned, spend time on those aspects of our work that are extendable or relatable to things beyond IDF curves and kind of can conceptually help folks think about how to incorporate climate information into future planning and design. So the first piece here is data selection. We used both historical observation-based data sets and projected climate model data sets. And in particular, we used, this is a bit of an acronym soup, this slide, I apologize, 4 projected downscaled climate model data sets. I'm going to go to the next slide to talk about those. I'm not going to talk about the historical data set in any detail today, but I thought it'd be helpful to talk about some of the trade-offs we looked at with the future projections. So in general, global climate models provide both modeled historic and projected future estimates of precipitation. They're often at course, at least the last archive of climate model runs that we use a lot in research and now in applied settings are at fairly coarse spatial scales. So about 1 degree by 1 degree, I think that's around 150,000 square kilometers. So these are big areas. I believe the state of Delaware has like 3, probably 2.5 if you did the area of them grids over it. So these are big coarse scale that aren't that helpful at the local level. The climate models do provide data from 1950 to 2100, so over a really broad range. As I mentioned, they both model the historic period and model the future. So it enables a comparison of apples to apples of what happened in the future to what could change in the past. The current archive called CMIP, the Coupled Model Intercomparison Project 5, includes 35 global climate models under a range of scenarios. So these scenarios are driven by varying assumptions of future atmospheric greenhouse gas concentrations. We call these representative concentration pathways, or CPs for short. And they essentially model scenarios of, if our current policies continue into the future and our emissions stay consistent with those, what could that mean for future climate? If our emissions dramatically increase, what could that mean for future climate? And a few kind of gradations in between or below. So that's what exists out there in terms of global climate model data. Because of the coarse spatial scale, that 1 degree by 1 degree, essentially grid that we get from the whole globe, there have been various efforts at local to national to international scales to what's called downscale that climate model data. And downscaled climate model data, I'm going to talk about the data sets we used in the next slide, but essentially tries to improve either the spatial resolution and or the temporal resolution so that you can get, instead of 1 degree by 1 degree grid, a 1/4 degree grid, or much, much finer. One of the kind of trade-offs when you're thinking about using these data is that a range of methods and a range of data sets exist. So we don't, as researchers in this space, make it very easy for kind of the average utility that wants to go out and pull a data set to know which one to choose. So what we did in this study is we looked at 4 of these downscaled data sets. You'll see them here. The data sets are listed in the leftmost column. BCCA V2, MACA, LOCA, and NA-Cortex. I said it was a bit of an acronym soup. I'm not going to read out the acronyms in their kind of full names. A, that will take a while, and B, they're not super informative. They give you a little bit of the underlying methods in the name, but just know there's 4 different data sets. They're kind of the first thing to note about these data sets is they offer varying spatial resolutions. So as I mentioned, the global climate model data is big and coarse, but these get down to really pretty good spatial scales when you're thinking about looking at climate changes at state to county levels, or even kind of at the sub-county level. They also offer, or they also come from a range of methods. There are 2 main families of methods for downscaling global climate model data. The first is statistical. That relies on essentially empirical relationships between the coarse grid cells that come out of the global climate model data and known values for precipitation or temperature at much more local scales. So those relationships are derived in different ways and then are reapplied to the global climate model data to generate higher resolution, essentially maps of temperature and precipitation. So that's the statistical. Dynamical methods essentially use the global climate model data as inputs to a higher resolution, dynamically based model. That's what this final data set does, NA-Cortex. And that enables the data set to also, well, it has a number of different trade-offs, but one of the benefits is that the NA-Cortex data provides both higher temporal resolution and spatial resolution than the global climate model data, although you'll notice it's not as fine spatially as some of the other data sets in our suite that we looked at. In terms of temporal resolution, I don't have that in this slide, but the first 3 are 24-hour temporal resolution, and NA-CORDEX offers 24-hour down to, I believe, 3 hours. So you get a much higher temporal resolution, which for things like IDF curves, for precipitation-based analyses can be really helpful at understanding some of these shorter duration precipitation events. So we incorporated all of these into our study. And part of the reason was that there are a range of trade-offs among them. And we had the computational resources to be able to look at a number of them and not just a single one. But as you're thinking about, or if you're thinking about incorporating, one or two, these are some of the trade-offs to consider: the spatial temporal resolution, the methodology. A couple other things to note, and then I'll move on past these. But is that LOCA, this third one, is what's used in the National Climate Assessment. It's probably the most widely used of these, followed by NA-CORDEX and then MACA. So if that helps kind of in the future think through the, at least, most commonly used of these data sets. That's one of the reasons we chose these bottom three, is because they're widely used. Okay, so we have a historical data set, and we have these 4 future climate projected data sets at varying spatial and temporal resolutions. And that was the input into our study. I'm going to walk through probably pretty quickly the various methods. I assume you don't all want to hear a presentation about generating IDF curves, but there are just a couple of things to note throughout. So I'll go through those fairly quickly. So essentially, the first step was generating IDF curves, given that's the topic of the work. And we did that by first testing some slight differences to the Atlas 14 methodology, but we really wanted the projected values that we were going to put into the final tool to be comparable and relatable to Atlas 14, given the widespread use of Atlas 14, despite its challenges. This essentially study created adjustments to Atlas 14. So we wanted to do some tests initially on how, on kind of the Atlas 14 methodology with both the climate model data as well as the historical data. That's all step one was. Again, I'm not going to spend too much time here on kind of what little nuances were slightly different, but we tested a few different things just to make sure when we were calculating IDF curves using the future projected climate data, we were doing so in a way that was, again, comparable and relatable to Atlas 14. So that was step one. Step two was essentially replicating the Atlas 14 methods on the downscaled climate model data. There's a lot of details here about how we did it. We used partial duration series. We used the L moments approach, which is what Atlas 14 uses. But the one thing to point out in this part of the analysis is that with the downscaled climate model data, we calculated IDF curves for a historic period, 1950 to 2000. This historic period is the same general period used for Atlas 14. And then we calculated IDF curves for 2 future periods, 2020 to 2070 and 2050 to 2100. These are 2 overlapping periods, but their midpoints are distinct and used by various entities we were working with through the Chesapeake Bay program for planning. So we wanted to make sure these future periods aligned with those that would be used by folks in the region. So we end up at the end of step 2 with an historic IDF curve for 1950 to 2000 based on the backcast climate model data and 2 future sets of IDF curves. So we end up essentially with 3 IDF curves. This is important for the next step, but I just wanted to make that point because we do utilize the historic period from the downscaled climate model data. And I'll talk about why we do that in the next step. So the third step was essentially calculating the change from that historic period in the global climate model data, from the IDF curve derived from that historic period, excuse me, and the two future periods. And a change factor, as conceptualized, is really the difference, the division between the future curve value and the historic IDF curve value. So if you have a 2-year, 24-hour storm event from the first future time period from 2020 to 2070, we would divide that by the IDF curve value for the same 2-year, 24-hour storm event from the historic period, 1950 to 2000. And what that gives us is a scalar. Essentially, this could be 1.2, which would mean that the future value is 20% greater than the historic value. If it was 1.1, it would mean that his future value was 10% greater. And if it was less than 1, like 0.8, it would mean the future value is actually less than the historic value. We didn't see many of those in the region, but that's how to interpret the change factors. And that's why we needed to calculate the historical data from the climate model, or that I should say, historic backcast data from the climate model data. So we can generate these change factors. It is not, we did not use, I get this question a lot, why didn't you use the actual observed data? We do, but what we do, and I'll talk about that in the next slide, we don't use that for the apples to comparison to say, by how much does the global climate model say climate is changing? That's what this step is intending to answer. By comparing the data consistently from the global climate model to the global climate model, we're able to see how much, using the same method, the same assumptions under that climate model, how much that model is projecting the future to change. And we'll bring back that historical observation data in a minute. So we created these change factors for each of the downscale data sets we used, for all 4, for every grid cell in our region, for each of the 2 future time periods. So we have a change factor for 2020 to 2070 and one from 2050 to 2100. For each of those future emission scenarios that I mentioned, we looked at 2 of them. And for each of the return periods. So we looked at 2-year to, I believe, 500-year. So that's kind of the core of the methodology. These change factors, I think, are important to spend a little bit more time on, just because this kind of conceptual relationship between a future value in a global projected global climate model data set to the historic backcast value is a way to think about how climate is changing in a consistent way across the same data set. Okay, and I'm just going to skip this about change factors, but they're kind of conceptually simple because they have that scalar relationship. 20% increase, 10% increase, 20% decrease is a really easy way to think about how climate is changing, and they're widely used. So that's kind of the only points those slides were trying to make. Okay, so uncertainty. The points I want to make here is that there are a range of sources of uncertainty when you're thinking about future climate. Each downscaling method introduces its own uncertainty because it creates a different relationship between that coarse resolution global climate model output and this kind of high resolution estimate you get from the downscale data set. You also have within each of these downscaled data sets a range of global climate models. So LOCA, for example, has 32 global climate models within it. And each global climate model within LOCA, just one of the downscaled data sets, is run under 2 representative concentration pathways, those future greenhouse gas scenarios. So you end up with, hundreds of estimates of future changes using this change factor approach for a given kind of point on the map. And so what we did is essentially present the full range that we saw. So for example, for a given grid cell, for a given downscaled data set, we could see a change factor that ranges from 1.1 to 1.3. So that would either be a 10% increase into the future or a 30% increase. And we don't assume a distribution across that range. We say, the 1.1 is just as likely as 1.3. And using this range of GCM, global climate models, future emission scenarios, and different methodologies, we can get a really good sense of what that full range of changes could be for that given point on the map. And this is kind of what that looks like. So if you're, this is an IDF curve for Chambersburg in the mid-Atlantic, or at least a Chambersburg station. And so what you're seeing here is the red line is the Atlas 14 IDF curve. So similar to that first figure I showed earlier on, you have depth on the y-axis, duration of the precipitation event on the x-axis. And this is just for the 2-year storm event, so the 2-year return period. So the red is the value we get from Atlas 14. This is based on historical observations. The blue area is taking that change factor, that 1.1, 1.2, 0.8, depending on what it is, and applying it to Atlas 14. And so by applying it, essentially just multiplying it by that value. So you can see here, everything, you see a range of values. So you see a light blue band, a dark blue band, and a dark blue line. So if we take the median of those hundreds of estimates over this point, Chambersburg, it's actually a station, then you, the median would give you the dark blue line. If you take the 75th confidence interval around that, you would get the dark blue band, and then the 90th is even greater. So this is how we're presenting uncertainty. So you see here, there's a range, at least when you get to the 24-hour storm event, of changes that could be seen for this particular IDF curve. And we present all of them, again, because depending on the type of infrastructure you're building, depending on the considerations for your region, if it's a high vulnerability area, if it's a really important asset, you may want to think about using something in the upper end of that uncertainty range rather than just the median, or thinking through what that full range implies for your management decisions. Okay, so that's kind of how we applied and thought about uncertainty for IDF curves. And then the other bit is just we present all the data in our final tool at the county scale. This was a request made by the region, given this kind of stormwater management and the way planning districts and various entities are organized, as well as some limitations in kind of how we think about and interpret the downscaled climate model data. Both we as researchers felt more comfortable, and our regional partners preferred county level change factors. So we provide these change factors that we've derived at the county scale. So each county in the region has a distinct change factor and an uncertainty band around it. Okay, so I'm going to show you a bit more of what all of this looks like in the actual online tool, and then open it up for questions. So if you bear with me, I'm going to switch to a browser. And so I'll walk you through kind of what this means in the tool. So this is our online tool that we built for users in the region to essentially look at how changes to future IDF curves are projected for their county. So in terms of what you're seeing here, this is the Mid-Atlantic. You'll see that there's a yellow line, that's the bounds of the Chesapeake Bay watershed. The areas around it are just the rest of counties that had overlapped with that line, with the exception of parts of Southern Virginia that were added, as I mentioned earlier, as an extension to this work. So the map is colored. The various kind of green colors are colored by change factors. So that, again, that scalar relationship between the future IDF curve value to the one over the historical period. In the tool, if a user forgets what change factor is, they can just hover over this little question mark and get a definition. So that's what you immediately see here. The little white location markers are individual stations. I'll just keep over this one, that we've already applied that change factor to generate a future projected IDF curve. So there are essentially two ways to get data from this tool. One is just the county level change factors themselves, by kind of what percent are we anticipating IDF curve values to change in this county. Or you can actually download the projected IDF curves themselves. So we offer those two options to users. I'll show you how to access those in a second. What's popped up here are the change factors for Delaware County. So you can see the range of options, or the range of values that we got for Delaware County. The median value was a 9% increase. The 90th percentile, so the upper bound that we provide, was 16%. And the 10th percentile, kind of on the lower end of the range, was only a 1% increase in this 2-year storm event. So that's how to interpret this part of the figure. So there's other options in the tool. A couple things to mention, just, I won't go through the details of some of the IDF curve selections, but we offer two emission scenarios. The high emission scenario, which projects typically greater changes into the future, and the low emission scenario. So again, one consideration could be, if you're looking at an infrastructure asset that's intended to last 100 years or 50 years, you may want to look at the high emission scenario as kind of a safety margin. Or if it's something that's a 5 to 10 year asset, maybe the low one, which is based on the current emissions trajectory, is more appropriate. So there's some kind of options to think about, when you're kind of applying and designing, an extension of something like this, or really just thinking about the trade-offs of climate model data in your own planning and design. Users of the tool can also select between the two future time periods I mentioned, one that's later in the century and one that's earlier in the century. Again, the time period you select could depend on the planning horizon you're looking at, could depend on the infrastructure asset you're designing. So there's options. You'll notice that the later time period, you see greater changes, so more blues. So closer to 1.3 for many of these places. So this Lee County, it's hard to see that one. Montgomery County in Virginia, you see 22% increase by the end of the century for this particular county. And then the only other thing to mention here is just, hovering over a county shows you the county level change factors. Clicking on an individual station, these white location markers, provides all the information for the actual IDF curve. So again, this is the change factor that's multiplied by the Atlas 14 value. That Atlas 14 value is from Atlas 14, so it's based on historical data. The data is also available in a tabular form. You can download it for every single station. There's various kind of comparison tables as well that you can access just to see, like, for example, the 3-hour storm here, the Atlas 14 depth is 1.3 inches. But when we're looking out, the median value into the end of century, the 2050 to 2100 time horizon, is almost 1.6 inches. So that's a bit of a difference when thinking about green infrastructure, whatever you may be designing or planning towards. I think I'm going to pause there, open it up to questions for the last 15 minutes. There's a lot more I could kind of go through with the tool, but just kind of wanted to show y'all really with this example, how we thought about uncertainty, how we presented it in this range in the chart, as well as in at the county level by showing both the median as well as the percentile ranges around it for the change factors, as well as how we use the change factors by comparing historic backcast climate model data to future projected and looking at that ratio and applying it to observation data rather than trying to compare directly climate model data to observations. So those are kind of the highlights I wanted to touch on with this work. I'm using this really as just an example of how we approached things. But happy to answer questions wherever is most helpful or relevant to y'all. So I will stop sharing. And then Richard, if you want to, I don't know if there are certain questions that have popped up that I could tackle first, or if we want to open it up.
Yeah, I think we have a couple, Michelle. So the first, I think, sort of relates to sort of which IDF curve to use based on the lifespan of your project. And I think maybe specifically with the emission scenarios, is there a rule of thumb or guidance on which one to choose based on your project or location or anything like that?
Great question. I get questions like this a lot. How do you choose in this uncertainty space what to use? Which, do you go with 90th, 75th median? Do you choose high or low? And there, there's no kind of hard and fast rule at all. A lot of it depends on the risk tolerance of the individual entity. Depends, on the asset you're trying to manage. I wish I could give you something more. It's actually, that was one of the limitations, I should say, of this work, is that we didn't have the time and resources we wanted to really develop that guidance in a meaningful way. And we're working on that actually right now on the side in separate work with Marisa. So we will be coming out with some guidance around that, like looser guidance that we're developing in collaboration with planners in the region, looking at how they've done it and how they've thought about it. But right now, unfortunately, I don't have any guidance other than saying if it's, a riskier or you're more risk averse, or that infrastructure is intended to last longer, it's probably worth thinking about and considering some of the upper ends of that bound or the higher emission scenario. It just, the trade-off is cost typically, because you're looking at a greater depth to then manage to.
Right. And I'm going to keep going here with the questions in the chat. If I butcher your question, feel free to step in. But this one relates to the statistical and dynamical downscaling methods that you used. Did you notice any large differences in the methods? And have you looked at the convection permitting dynamical downscaling methods to see if there are significant differences in the results?
Yeah, great question. So to the first part of the question, so these are existing data sets. We didn't actually do the downscaling ourselves. So that's one, which was nice, one fewer thing to do in this work. What we did do is explore in the initial when we initially started generating these change factors, what the trade-offs were between the different data sets. So we looked at the LOCA data set, we looked at the MACA data set, we looked at NEIWPCC separately before combining them to just make sure they made sense. And what we found actually is that for this region, the MACA downscaled data set and the BCCA V2, which were the first two in that slide, didn't really make sense. They had patterns that weren't really consistent with climatology in the region. So you would see drying along the coasts or weird behaviors at higher elevations. And we didn't feel comfortable with the change factors those were providing. So we actually took those out of the final data that's produced in the tool. So what's actually shown in the tool is just NEIWPCC, the combination of NEIWPCC and LOCA. Those were consistent with one another. They're consistent with just known patterns of how precipitation kind of works in this region. So that was kind of one thing we did in part of our analysis. In terms of other downscaling methods, I'm not familiar with that particular one. But it's, you know, always exciting to see, especially on the dynamical side, new methods coming out that can really help improve both, as I mentioned, the spatial resolution, which is what a lot of the statistical methods do. But on the dynamical side, you often get advancements or enhancements, I should say, in the temporal frequency. And that, especially for precipitation, is so helpful. So I'm excited to see that work, and I'm not familiar with it right now. That's a great question.
Yeah, thanks, Michelle. So the next question, I think, has to do with the broader applicability of the tool. And so specifically, two questions into one here, is that, you know, obviously it's using some greenhouse gas emissions information to develop the tool, but there are some sort of local different impacts to those emissions. So can the tool just be broadly applied to other regions of the country or the world, or what would be involved in making that happen? Or is that already planned? And is that already planned?
Yeah, good question. So the emission scenarios are global scenarios. So what we've done, what the downscaled models have is, maybe stepping back a bit. So there's various layers of this data analysis, right? There's the coarse resolution global climate model data that's then downscaled using either a dynamical or statistical method to a local level. The two emission scenarios we used are assumptions that drive the global climate model data sets, a global high emission scenario and a global kind of current policies scenario, and then kind of a range in between. And so these scenarios are kind of a standard that's used across climate science around the world so that we can compare data sets, we can compare changes between regions, and we kind of have this standard set of inputs to the global climate model. So there's some consistency in what we're doing and how we're thinking about planning. So this general methodology and these general data sets are widely applicable across the US, especially NA-Cordex, that one particular downscaled data set specific to North America. LOCA and MACA are both just for, I believe, just the continental United States. And BCCAV2, I think, is also just continental, but it may include Alaska and Hawaii. And so this method and those data sets could be used anywhere else in the United States. And we would love to do that work and could essentially replicate the exact same methodology anywhere in the US. But those particular downscaled data sets are not available internationally. So we couldn't do that internationally, but the same emission scenarios are.
That's helpful. So, and I think also related to this, there are, of course, different considerations for coastal areas versus inland areas. And so can you talk a little bit how the tool deals with those two different, you know, parts of the region, the world, the country? Yeah.
So we kind of in terms of management and planning, they're absolutely very different flood conditions and considerations in coastal regions, because you have the combined effects of tidal flooding and sea level rise with precipitation-based flooding. This tool does not take that into account. So it's only adjustments to precipitation-based IDF curves. That's a whole nother area of research and work, which is fascinating. I have colleagues doing some of that work, and I know it's a big need for a lot of these regions, particularly in the mid-Atlantic and along, well, actually probably for most of the coastline of the United States. But this does not directly take that into account. It's just adjusted IDF curves.
No, that's really helpful. And I know that we do have a few more minutes left. If anyone would like to put a question in the chat or even unmute to ask your question, But I do know, Michelle, you were happy to share your contact information with folks if they have additional questions.
Yeah, absolutely. I will put my email in the chat as well as the link to this tool so that, if it's helpful, you'll have it right now.
Thank you.
Mhm.
Yeah, so we'll give 15 minutes for station identification here and make sure everybody's still on the National 303D TMDL webinar and see if anybody has any other questions. Well, seeing none, Michelle, thank you for your time today. It's really helpful, I think, to the TMDL community across the country and around the world. And we really appreciate the information.
Yeah, well, thank y'all for joining, and please feel free to reach out if additional questions come up.
Thank you. Have a great day, everybody. And again, this presentation will be posted on the website and our illustrious YouTube channel, along with the actual presentation. So enjoy the rest of your week, and be well and make good TMDLs and implement them.